So v of 1 is -3. What are the units on v of 1? -3 what? Meters per second. So if it's -3 meters per second, what direction is that thing going in? South. It's going south. So it's the velocity at time 1. Excellent. What about this right here? It says, can someone read that out loud? What does this say? If you had to read that out loud, could you tell me how to read that out loud? Can anybody read that out loud for me? The something from something to something of something? The integral of
v of t
from
0 to 2.
Yeah, so you're doing the area under the curve of v of t from 0 to 2 using n equals 50. Did you use your web applet to do that? Anybody get it? What did you get, Morgan? Do the left one. What's the left one tell you? -5 point something.
-5.333 is the actual.
No, but what's the estimate gonna be? 4128, I think.
Yes.
Did anybody get that? What are the units on this, everybody? When you do the area under the curve of velocity, what are the units here? So if you go, what's the derivative of velocity? It would just be meters, yeah. So the derivative of velocity is acceleration, meters per second squared. We're going in reverse, so this is meters. So what does this say realistically? This means that from time 0 to 2, the particle what? Or is it a car? Is it a car?
Person.
The person ends up where? 5.4128 meters what? South. Meters south. Here's the key. You see the negative right there? We just calculated quote unquote area under the curve, but the area came out to be negative. If the area comes out to be negative, it means that the person has moved what direction? Moved, in this case, south, but in general means backwards. If one direction is forwards, another direction is going to be backwards. The key is we can calculate negative area, and this is a misnomer because theoretically, can area be negative? No, but we say it out loud because it's easier to say when we calculate these integrals. When we calculate these integrals, you have to be really, really careful. So when you did that out, on your program right here, you ended up with something that looks like this, I think. You got this? So it's underneath the x-axis. So if you're adding up rectangles that are underneath the x-axis, that means in this case you're moving south. You're moving backwards. Now what happens, what does this graph do? This graph continues like this. Where do the rectangles get drawn if I go to the right of 2? Where do the rectangles get drawn if I go to the right of 2? So x continues there. Where are the rectangles going to be?
Above the x-axis.
They're going to be above the x-axis. Exactly. The rectangles are all going to be up here, right? Meaning the person is going to be moving to the north, moving in the quote-unquote positive direction. If you add together all of these things, you end up with something called displacement. Displacement and distance traveled can be the same thing as we explained last class, but they sometimes aren't. So for example, if I go 10 million miles that way and then 10 million miles back, what's my displacement? 0. But what's my distance traveled? 20 million miles. Displacement and distance traveled are the same thing if you don't what? They are the same if you don't what? Backtracking, turning around, exactly. So displacement and distance traveled are the same as long as you don't turn around. Now, are particles going to turn around? Are people going to turn around? Are cars going to turn around? Sure. So you have to be very careful about this. So let's investigate a little bit more. Let's take a look at this graph right here. Positive or negative from 0 to 2? Calvin.
Positive.
Why do you say that?
Because it's above the x.
Yes, this is above the x-axis, that blue region. What about, let's say, from 2 to 4? What would that be? Anybody want to guess? Just say it out loud. It's all negative because it's all below the x-axis. It's all below the x-axis. What about from 0 to 6 Henry? What about from 0 to 6 Henry? If I went from 0 to 6, do you think it's going to be positive or negative?
Negative.
Why?
More of it's negative than positive.
Exactly. More of it's negative than positive. And in this case, you see how much bigger that green region is than the blue? It's pretty clear, even though I hate using the word clear, because either it's clear to you and you don't need me to point it out to you, or I say it's clear and you're like, no, it's not, and then you feel bad. I hate the word clear in mathematics. I hate it, I hate it, I hate it. Because, let's say I asked you, Jen, instead, the integral from, let's say, 0 to 3.5 of f of x dx. Why is that much harder to answer on this one? Is that positive or negative? Jen, why is that one much harder?
Because part of it is in the negative and part of it is in the positive.
Yeah, so we did that before on this one, like on C. C was easy to answer, but what happens if I asked you about from 0 to 3.5, like to here, right here? Why is that much harder to answer if it's positive or negative?
It's not all negative and it's not all positive.
And it's not clear which one is bigger, right? In this case, the green is much bigger than the blue, right? But if I were to take this purple region right here, or you can't really tell because it looks like black dots, but is it clear, quote unquote, if that's bigger or smaller than the blue? No, not at all. So if I ask you relative questions like this, it'll be really, 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 really huge and small. In this case, really big green and smaller blue.
So what does it find?
So without using a computer program. Take a look at this one. Evaluate the integral from 0 to 2 pi of sine x dx without using a calculator or a computer. Think about that one. Don't write anything down. Sine starts at the origin, and what does it do? Go up or down? Goes up, down, and then up. There's 0, there's 2 pi. What do you know about this area compared to this area right here? They're the same. So if one is above the x-axis and one is below, what happens when you integrate across 0 to 2 pi? It comes out to be what? 0. 0. It comes out to 0. So when you get, we are going to learn a way to algebraically do this, not just using a calculator, but you need to not forget your geometry. I think I emphasized that last class.
Yeah.
You need to remember, like, you know that sine is symmetric across pi, right? So you know it's the same above and below, so it's going to be 0. There are really hard integrals that if you try to do by hand are almost impossible, but if you remember basic geometry, you can do them like that really, really quickly. For example, the area of a circle, pi r squared. How many of you remember pi r squared is the area of a circle, right?
Yes.
That's an amazingly useful thing to have, right? But here's the thing. Can you prove to me that that's true? Can you prove to me that the area of a circle is pi r squared? It's actually really hard to prove. What do you think you need in order to find pi r squared? You need calculus to prove it. It's actually an integral. And this is what you're actually adding up, just as a side note, everybody. As a side note to what I just said, here's a circle. Yay, there's a circle. I draw the center of the circle, and if I bring out all of like these spokes, what shapes do I have right there? Triangles. So it goes all the way around. If I add up all of those triangles, I have an estimate for that circle, correct? The area of that circle. What happens as I make the triangle smaller? The estimate gets bigger. So what did we just do? We just added up rectangles. You can do calculus with other shapes. You can add together rectangles or other shapes. So if you do that integral, you can end up with pi r squared. It's not easy, but you can do it. But what do we use first? We use pi r squared before we prove it. Okay, so this is what I'd like.